regarding the example that we started, which is related to exponential distribution, we started with finding the average, and we said that, okay, we have x and then multiplied by the PDF. And if you integrate by parts, we get basically this as the average, and the mean square value, if we have x squared multiplied by the PDF, and we do the integration by part twice, we get this value. Now the variance is the mean square value, which is the second moment, minus the mean squared, which is basically the second quantity minus the first quantity squared, which gives you b squared. And we said that, as we can see, if b is large, this is basically the graph that we compared large b with a small b. So this is a small b, and this is a large b. Large b has the PDF wide, and hence the variance is large, as well as the mean, by the way, in this case. Now, if you would like to calculate the skew, then basically we need to calculate the third moment. Third moment, you can calculate the skew directly from mu3, which is basic expected value of x minus x bar to the power 3, and do it in the integration directly. Or we calculate m3, and then we try. So basically the skew, which is mu3, equals this, which if we open up the cube, x minus x bar to the power 3, all 3 to the power 3, then we have this basically inside. Now this is m3. This we have found them before, m1 and m2. These have found before, and this is m1, the cube. So the only missing is m3. m3 is expected value of x3, so basically we get x to the power 3 multiplied by the PDF, which is fx. And again, integrating this by part, I think 3 times, we get this long expression. So now, putting all these together and simplifying, we get basically this q equal 2 to the 2b cubed. Now, if we would like to find the coefficient of skewness, if you remember, coefficient of skewness is defined as the third central moment, mu3, divided by the standard deviation to the power 3. So the mu3 is as we have found it here, and the standard deviation is the square root of the variance, which is square root of b, so it's b cubed. Standard deviation is b. It's the standard. It's basically the square root of the standard of the variance that we have found before, which is square root of b squared, which is b. So standard deviation to the power 3 is b cubed, and dividing this we get 2. And we said that if we have a positive skewness, means that it's skewed towards left or right, Shima?
Right.
No, it's left. So we said that here, if you remember, skewed to the power left, towards the left, we have positive skewness. Skewed to the right, we have negative skewness. So try to remember the opposite way or whatever. Okay? Any question about this example? Let's have another example about uniform random variable. So we have a uniformly distributed random variable between 2 numbers, a and b. So what does the PDF look like, Shabab? A and b. How does the PDF look like?
Like a rectangle, because uniform.
No, the PDF. Rectangle is the CDF in this case. From the name, uniformly distributed, equally distributed. So how does it look like?
Rectangle.
Rectangle, exactly. Oh, sorry, you said rectangle. I heard the triangle, sorry. Yeah, it's rectangle. Thank you very much. I heard it there. I don't know. Sorry for that. So yeah, it's rectangle, exactly. And what is the amplitude here? The amplitude is
B minus 1 over B minus A.
b minus a, so that we ensure that the area under the curve is 1. So now, and in terms of analytically, we can write it as 1 over b minus a between a less than or equal x less than b, and 0 otherwise. Right? So now, in order to find the mean is expected value of x, right? So simply, it's the integral from minus infinity to infinity. We start with the definition, right? Now we use what is fx. What is fx of x? It's 1 over b minus a, right? However, this is only in the range of a to b, and we still multiply x as it is, dx. Okay. Now this is a constant. So we have here x squared over 2 multiplied by 1 over b minus a, and this is from a to b, right? So we have here b squared 1 over b minus a multiplied by b squared minus a squared over 2. Now you can leave it as it is, or you can simplify. What is b squared minus a squared?
b minus a, b plus a.
Exactly. And in the denominator we have 2b minus a. So you can see that these two terms cancel, and you end up with a plus b divided by 2, which is the midpoint. X bar is the midpoint, and you can expect that, right? Because it's uniformly distributed, it's equally distributed. So there is no reason that the mean will be different. Now, is it equal to the median or what? ايش رايكم, equal or لا?
Yeah, it should be.
It should be, because it's symmetric around the mean, right? So this is related to the mean. Now, what about the variance? In order to find the variance, it's better to find M2 first, which is expected value of x squared. Okay? Expected value of x squared, again, it's by definition x squared fx of x. So whatever inside here, we bring it here, which will be 1 over b minus a x squared dx. Sorry, yes, x squared dx from a to b, which will be x cubed over 3 from a to b divided by 1 over b minus a, which will be b cubed minus a cubed divided by 3b minus a. Anybody knows how to simplify this? شباب؟ يلا algebra.
Yes.
Algebra, yes.
B minus A, then
Yes.
another bracket.
Yeah.
B square
B square
minus,
Yeah.
I think,
minus
Plus
AB
B A B, yes, plus A
plus
square.
AB
Plus a square,
plus
right?
Yeah.
And this is divided 3b b minus a. You can see that this cancels this, and you end up with this. Okay. I think you can complete the square here, and then you can simplify. Anyways, so now what do we have here? So basically, sigma x squared will be what? It's expected value of x squared, x minus x bar square, right? Or we have already found that it's m2 minus x bar square, right? Which will be b minus ab plus b square, sorry, a square divided by 2, so half of that, minus a plus b square over 4. Right?
Doctor, it should be plus AB.
Plus AB. Plus here, yes. Here plus.
Yes, plus doctor.
طيب ممتاز. شكرا. So now you can simplify. I don't want to waste my time in the simplification, but anyways, here we have what? A squared, this will be basically 1 over 4, and we have here A squared plus 2AB plus B squared, right? So we have here 1/4 A squared, here we have 1/2 A squared. So you can simplify them together. You will end up with, I think, A plus B squared, A minus B minus, I think B minus, I'm not sure about the final result, but it will be, I think, B minus A squared divided by 12 or something like this. Okay, so the rest is algebra. Any questions, Shabab? Any question? So what about if we have discrete? We have, for example, PDF looks like this. -1, 2, خلينا بس نغير الأرقام. We have, and we have here at 1. Let's say we have here 0.3, 0.3, 0.4. Right? This is a PDF. Find the mean. Find, so the expected value of x squared. Here M2. How do we do it?
We will have a series instead of the integral.
It's exactly, it's a summation from I equal 1. How many values we have here for x? How many values does x take? 3 values, right?
3 values.
Of x I squared. So whatever here, we square it. And then probability of xi. So here we have the first xi is -1 squared multiplied by its probability. What is the probability of -1?
0.3.
Yes. And then the next value of x is what? 1 squared multiplied by its probability. What is the probability of 1?
0.3.
Yes. And the last one is 2
square
yes.
multiplied by 0.4.
Excellent. And you can solve it. Okay, so we have here 0.3 plus 0.3, which is 0.6, plus 4 multiplied by 0.4, which is 1.6. So it will be 2.2, right? Okay, so this is the way we do it for discrete. Any question? So now we'd like to talk about some inequalities. Sometimes you don't have the PDF. So in order to find, for example, the probability that x is, if in order to find the probability that x is less than a certain number, in order to do this, you need basically to integrate from -infinity to a fx of x, right? In some applications, we don't have the PDF. We don't have it, not there. So, however, we are interested in not exact probabilities. We are interested in roughly what is this probability is. This is important in the rough or the bounds, we call them, are important in many applications. Either estimation, when you want just to estimate the probability, or if you are interested in the simplifying of certain problem. So basically use your bound to make the problem simpler and try to solve it. So either for mathematical simplification or for estimating of the probability, not exactly what the probability exactly is. So in this case, we will talk about 2 inequalities. The first one is Chebyshev inequality. Chebyshev inequality is related to calculation of the following. The probability that x is away from its mean x is away from its mean by larger than epsilon. So if this is the PDF, if this is fx of x, and this is the mean, then what we are trying to find is what is the probability that x is away from the mean by larger than epsilon. So this is x bar minus epsilon, this is x bar plus epsilon. What is the probability that x is away from the mean by more than epsilon? Okay, so this is equal to the probability that x is away from its mean, x bar, by more than epsilon. This is the way we read it. Now, you can calculate this by basically integrating, right? And so on. However, as you mentioned, in many cases, in some cases, you might not have the PDF, or you are interested only on a rough estimate of this probability. So this Chebyshев inequality gives you this rough estimate. It tells you that this probability that the random variable x is away from its mean by more than epsilon is upper bounded by this number, which is sigma x squared, the variance squared divided by epsilon squared. We call this upper bounded. This is the way we read it. This probability is upper bounded by, so it's bounded from the top by variance squared by variance divided by epsilon squared. Let's try to prove it. Maybe you will be convinced. So what is sigma x squared? Sigma x squared, by definition, is the integral of x minus x bar all squared multiplied by the PDF from minus infinity to infinity, right? Which is larger than integrating over, this is a positive PDF, right? The PDF is a positive function. And this is a positive function, which is اللي هو square هذا. And because both of them are positive, the whole thing is positive. Then integrating over the whole range from minus infinity to infinity is definitely larger than integrating over the specific range, which is the range that is shown in the yellow curve here, in the yellow part, which is x minus x bar larger than or equal epsilon. Okay? So this integral is definitely اللي هو integrating over minus infinity to infinity is larger than integrating over a specific range. However, over this specific range, another range, if I replace whatever inside here, we know that within this range, this is larger than or equal epsilon squared, right? هذا الأخضر is larger than or equal epsilon squared by definition of the range. Within this range, x minus x bar squared is larger than or equal epsilon because the range states so. And hence this integral is larger than epsilon squared multiplied by this integral. And this integral, we know that this is what? Integration of the PDF over a specific range, which is by definition the probability that x lies in this range. It's the probability that x lies in the same range. The same range. Let me just plot the range. It's the probability that x lies within this range. So now collecting this together, just dividing by epsilon, we can see that this probability is less than or equal sigma x squared divided by epsilon squared. واضح يا شباب؟ Any question about the meaning of Chebyshев inequality and how did we prove it? واضحة؟
Yes.
Just to clear.
طيب, you can see that the probability here is proportional to sigma x squared. So you can see here from this plot, the probability that x is away from epsilon, هذه اللي هي shaded yellow, increases as sigma x squared increases, right? صح? As sigma x squared increases larger, this probability that x is within epsilon, away from, sorry, more than epsilon, also increases. Right? So basically the Chebyshev inequality makes sense. We're not, although we did it, we proved it mathematically, but also it makes sense. As the sigma x squared increases, the PDF becomes wider, and hence the probability that x is away from its mean by larger than epsilon becomes larger. This is one thing. The other thing, if we fix sigma x squared and we increase epsilon, okay, so epsilon is, so basically we are saying that the probability that x is away from its mean by more than epsilon، ايش رايكم تزيد ولا تنقص لما epsilon تكون اكبر؟
decrease.
It will increase, decrease. ليش؟ لانه epsilon اكبر، epsilon تصير هنا، فالبروبابيلتي حتصير اقل. واضح يا شباب؟ So it's proportional to sigma square, it's inversely proportional to epsilon. Okay? Now, if we look at it from the other way around, if we are interested in the other probability, which is the probability that x is within epsilon from the mean. So this is the probability, هذا العكس. X is within epsilon from its mean. X bar. هذه the probability. In this case, this will be larger than or equal 1 minus x, variance divided by epsilon squared. We are talking about this probability, اللي هو الآن this yellow curve in the second graph. The probability that x is within epsilon from the mean. This is larger than or equal 1 minus sigma squared divided by epsilon squared. Now, if we take sigma to 0, sigma squared to 0, what do we get? We get this probability approaches 1. Sigma squared to 0 means what? Means sigma becomes يعني كده تصير مرة نحيف. In this case, this probability هذه هي الآن x bar وهذا x bar plus epsilon وهذا x bar minus epsilon. This probability goes to 1. ليش? Because it will encompass mostly all the probabilities. So as sigma squared goes to 0, means that the PDF becomes narrower and narrower, focused around the mean. Okay, شباب? Any question? Now let's have an example of the Chebyshev's inequality. Find the probability that a random variable, you see here, a random variable. We did not tell you it's a Gaussian or uniform or exponential or whatever. This is for general random variables. Any random variable without knowing the PDF, what is the probability that the random variable will exceed will be away from its mean by more than 3 epsilon, more than 3 standard deviation. So what we are asking here, the probability that x is away from its mean by more than 3 standard deviation. Now this is by using Chebyshev inequality is sigma x squared divided by epsilon squared. هذه هنا هذه epsilon squared. What was epsilon? 3 sigma, right? So epsilon squared is 9 sigma squared. So sigma squared cancels sigma squared and gives you 1/9. Okay? So the probability that x is away from its mean by more than 3 standard deviation is maximum 1/9. And you can see here, we are plotting here, if this is x bar, we are plotting here x bar plus 1 sigma x, x bar plus 2 sigma x, x bar plus 3 sigma x, and so on in the other way, x bar minus sigma x, and so on. You can see that here 3 sigma x squared, 3 sigma x, sorry, most of the PDF, for example, for the Gaussian, 99% of the PDF is within this 3 sigma, within 3 sigma from 2 directions, which doesn't contradict with this. This says the probability that you are away from that is at maximum 1/9. 1 minus 0.997 is less than 1.9. Any questions about? طيب, a related inequality is the Markov's inequality. Markov's inequality will not prove it, but it has the same concept, and even the proof uses the same concept of the Chernoff inequality. Markov inequality only works for x non-negative, so only non-negative random variables. So x has to be non-negative, means that it goes from 0 to any number, but it cannot be negative. So the probability that x is less than x is 0 is 0. In this case, the probability that x exceeds a specific number a, is upper bounded by the mean divided by a. Okay? It's upper bounded by the mean divided by a. This is used when the PDF is not given, but we have the average. It has the same concept, but it's different result, I would say. The last thing that I would like to start, and we'll continue next time, is what we call moment functions that generate moment. Functions that generate moment are very important functions that complement the concept of PDF. The first one, they are both the two functions that we'll discuss that give moments. One of them is called the characteristic function. The other is called the moment generating function. They are almost the same. They are very, very related. We'll talk in a minute why do they give moments. Let's see. Characteristic function is defined as this. Phi x of omega equals expected value of e to j omega x. What does this mean? Well, it's a purely mathematical thing, so it doesn't have any physical meaning, the characteristic function, except that it helps us in generating moments. I will give you in a minute how. So it's expected value of e to j omega x. What does this mean? It means that we put this here next to the PDF and integrate, right? This is the way we do it. What is this, Shabab? What do we know about this? Where did we find it? We see it before.
Fourier transform.
Fourier transform, right? So this is the Fourier transform. The characteristic function is the Fourier transform of what? The PDF. So if you take the Fourier transform of the PDF, we get what we call the characteristic function. And vice versa, the PDF will be the inverse Fourier transform. So basically, a characteristic function of x of omega equals the Fourier transform of the PDF. And vice versa, the PDF is the inverse Fourier transform of the characteristic function. Okay? Now, the first thing that we'd like to note is that the characteristic function is always upper bounded by its value at 0. Why? Because if we take the absolute value and we take the absolute value of, this is less than the absolute value of the individual, using the triangular inequality, the absolute value of the characteristic function is less than or equal to the absolute value of the PDF alone and multiplied by the absolute value of e to j omega x. And we know that this is less than or equal 1. Right? The absolute value of e to j, any exponential, is always upper bounded by 1. Any complex exponential is always upper bounded by 1. And hence, this is less than or equal the PDF. And the integration of the PDF equals 1. Now, what is 1? 1 is equal to omega x at 0. Omega x at 0 equals expected value of e to j omega, so e to j 0 x, right? But what is e to j 0x? So
1.
1, right?
1 yes.
Which is 1. So this is equal to the center point of the characteristic function. So the maximum of the characteristic function happens to be at 0, at omega equals 0. Now let's see how to use the characteristic function. If we differentiate the characteristic function n times, okay, if we differentiate the characteristic function n times and set omega to 0, what does this mean? Differentiating with respect to omega, right? So differentiating e to j omega x with respect to omega, what do we get? Every time we differentiate e to j omega x with respect to omega, what do we get?
We will have jx e to power
Jx,
j.
exactly.
E to power j omega.
Exactly. So every time we differentiate, we get jx. So differentiating n times, how many jx we get?
njx.
Yes. No, not n. It will be j to n, x to n. Because every time you differentiate, you will get new jx here. Okay? واضحة يا شباب؟
Yes.
Now setting omega to 0. What does setting omega to 0 means? Means that this will be what? 1, right?
Will go on yes.
e to j0 is 1. So what do we have here? We will have j to n, which is constant, طلعناه برا, the PDF نفسها, and x to the power n. But what is this by definition?
Momentum.
Exactly, this is the nth moment. So what do we get here? We get the nth moment equals what? Equals the derivative n times, which is this one, set with omega set to 0, multiplied by, sorry, divided by j to n, which is multiplied by, كأنك ضربتها, if you multiply by it will be minus j to n. So this is the way we find the expected value of x to n. واضح؟ طيب شباب, start operating your cameras.